Previously, we introduced the second law of thermodynamics by stating it in a very specific way. In this lecture, we're going to discuss the general version of the second law of thermodynamics that is defined by using a concept known as entropy. Now, before we get into what the second law of thermodynamics is in its general form, let's discuss this concept of entropy, what it is, and how we define it. So when an amount of energy is added into a system by a reversible process, the change in entropy of that system is defined in the following way. So if our temperature is assumed to be constant during that process, then the change in entropy given by delta S is equal to Q divided by T, where Q is the energy that flows into our system and T is the temperature given in kelvins. Now, what happens if the temperature during the process is not constant? So if we're dealing with a non-constant temperature, that means we have to talk about infinitely small changes in our entropy. So at that particular moment in time, the infinitely small change in our entropy given by ds is equal to the infinitely small change in our energy that flows into our system divided by the temperature at that instant in time. Now, let's suppose we take our system and we take it from an initial state given at A to a final state given at B. So that means we can define the change in entropy during that process when we take our state from A to B in the following way. Delta S is equal to the integral of the infinitely small change in our entropy taken from A and brought to B. Now, because ds is equal to this ratio, we can replace ds with this ratio and we see that delta S is equal to the integral of dq divided by t taken from A and led to B. So this is our change in entropy for a system taken by a reversible process from some state A to some state B. Now, in the next lecture, we're going to discuss the fact that entropy is a state variable. We're going to see why it's a state variable, and we're also going to discuss what a state variable is. In this lecture, we'll just mention that entropy is in fact a state variable, and what that basically means is the change in entropy as we go from some state A to some state B is pathway independent. It doesn't matter how we go from A to B, the change in entropy will always be the same. So entropy is a state variable. Now, let's look at the following statement and then let's see why this statement is true. So for an isolated system is essentially a system in which mass and energy does not flow into our system and does not leave our system. So for an isolated system of two objects, the transfer of energy from the object at the higher temperature TH to the object at a lower temperature TL increases the total entropy of that isolated system. So let's see exactly why by looking at the following scenario. Let's suppose we have two objects, and these two objects is our isolated system. So we have an object given by H at a higher temperature TH and an object that is cooler at a lower temperature given by TL. Now, initially, energy begins to flow as a result of heat, as a result of a difference in temperature. So we connect the two objects and heat begins to take place. Now, the object eventually comes to thermal equilibrium. What that means, the temperature will eventually equalize. This object will gain a certain amount of energy, and this object will lose that same amount of energy. So let's represent the change in entropy of our isolated system that consists of these two objects. The change in entropy is equal to the change in entropy of this object plus the change in entropy of this object. So delta SH plus delta SL. And let's go back to this formula. So the delta S is equal to Q divided by T. Now, this object loses energy, and let's say it loses negative Q energy. That means this object must gain that same quantity of energy because we're dealing with an isolated system. So we have negative Q divided by this temperature plus positive Q divided by this temperature. Now, what exactly is this temperature? Well, this temperature is simply the temperature, the intermediate temperature between TH and the final temperature. So TF is the final temperature that is reached when the objects are brought into thermal equilibrium. So T intermediate temperature between the H, the high temperature, and the final temperature, and this is the intermediate temperature of this object between TL and the final temperature. So our range is given by the following. We have our temperature intermediate between the H and the F for this object is between the final temperature and the high temperature, while this temperature is between the high and our low. Now notice, this quantity is greater than this quantity, and this will become important in just a moment. So let's rearrange this equation, and let's take out the common term, let's take out the Q, and we get the following result. The delta S, our change in entropy, is equal to Q multiplied by the difference in the two fractions. So we simply rearranged these two fractions. So 1 divided by the intermediate temperature of this object between the final temperature and the low temperature. And this temperature is the intermediate temperature of this object between the high temperature and the final temperature. Now notice, this lower denominator is greater than this. That means this fraction will be less than this fraction. So the difference of these two fractions will always be positive. So that means because this difference is positive, Q multiplied by positive will always be a positive. And we see delta S must always be positive for a isolated system. So the total entropy change in any isolated system is always positive. And this leads directly into the general version of the second law of thermodynamics, which can be stated in one of two ways. So let's look at this version. The entropy of an isolated system never decreases. It either remains the same, and that is only true for reversible processes, or it increases, and this is true for irreversible processes. Now, because reversible processes don't actually exist because they would take an infinite amount of time, that means we can restate this version in the following way. So the total entropy of any system plus the entropy of the surroundings always increases in any real process. So that basically means that we define the second law of thermodynamics using this concept of entropy.